Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. We're going to start the stream today with a question we got because it's actually very germane to what we're doing here on day 437. The question was, I was watching the previous stream, it came from the chat. I was watching the previous stream about getting better noise sampling and wondering why you need any randomness if you obtain a pretty and evenly well-covered sampling hemisphere. I think that's a great question. I think I kind of mentioned the answer when we were talking about lighting before, but we didn't really harp on it, and it is important, I think, to harp on it simply because it is an important thing to understand about sampling. And so let's talk about it. Okay. So what we need to talk about is undersampling specifically and the consequences of undersampling, because that's all we're dealing, that's the whole thing we're dealing with here, right? Our problem is that we have a system that we know we could get perfect results from if we just threw a ton of samples at it, right? And we saw that happen when I turn on the accumulation version and we just let, 60 frames or something accumulate. We end up with a nice, pretty stable lighting solution, right? So we pretty much know for sure that there's no problem with the algorithm if it was offline. Our problem is with running the algorithm on too few of samples, right? Having it have to produce a lighting result without being able to sample as much as it wants to. That's all we're doing, right? So the question that the person had on chat is, well, why can't we just not use random samples, right? Why can't we just say like, all right, if I'm sampling here and I just sample out in a few equally spaced directions, and I know that that won't have any noise because, it's not changing the sampling directions, isn't that sufficient? Can't we just stop there, right? And the problem with this is because it's, and again, the reason I wanted to kind of open talking about it is because it's critical to understand what the function's domain is that you're sampling and what will happen if you undercover certain parts of that domain as a result. Okay? All right. So let's look at this. Lighting for our hemisphere is talking about sampling a function that looks like this, effectively, right? We have a hemisphere and that hemisphere for the surface we could parameterize with two angles, right? We could look at it as like how far around the hemisphere you're going, and then how far up, let's say. Really anything we want, it doesn't matter. There's just 2 degrees of freedom. It doesn't matter how we parameterize it, but there's 2 degrees of freedom to create a hemisphere, right? And we could talk, they could be anything. They could be X and Y, and then you just normalize Z, right, or something, right? So it doesn't matter what you put here, I don't care. Just any 2 parameters that get us so that if we did the whole range of them, right, like in this case, like 0 to 2 pi, and 0 to pi over 2, right? Because you can only lift it up that high, right? If we just do something there, I don't care what it is, as if you densely sampled it, you would get the right answer. And then we have time, right? Now, why do I include time in here? Well, I include time in here because this function changes over time. There's, a light, and that light doesn't stay here necessarily. That light may move over here over the course of a second, let's say. And so as it moves, we would expect the lighting answers to change, right? They're not going to be the same. All right. So let's suppose we hold t constant. So our game is not moving. It's just a static scene. In the case where it is just a static scene, what happens to our domain sampling, right? We're sampling the hemisphere. I'm going to look from top down because it's just easier to talk about it. We don't need the extra dimension, really. So we can even just think about one of these dimensions at this point, which is theta, right? So as I'm sampling, what I'm doing is I'm looking out into the world and I'm seeing the sorts of things that I hit out here. And sometimes, because of the sampling density, I will miss things entirely, right? I just won't hit them. Make sense? Now, normally, if we were doing ray tracing for reals in an offline renderer, we would be ray tracing from way more points than we're ray tracing from right now. Right now, we're only ray tracing from, like for example, one little point here at the center of this big reflector, right? Or maybe 4 points, one in each corner or something, right? But normally in a ray tracer, we'd be tracing from lots of individual little points, right? And so the question of, if we were to take randomness out of the system, right? Because randomness means that every time we sample, we will get slightly different answers if we're undersampled, right? Because sometimes we'll hit things, like sometimes we'll randomly hit this, and sometimes we randomly won't. That leads to noise in the answer that we see, right? So as these vectors jitter around, sometimes they hit brighter things, sometimes they hit darker things. That's the source of the noise. So what the person on the chat's proposing is, like, why don't we just not do that? So the first answer is because, okay, something not relevant to our game, let's say this were just an offline ray tracer, what would happen is the noise that you now no longer see in terms of the changing brightness of a particular point goes into noise across points. So this point and this point and this point will all hit differently, right? So some of them will be brighter and some of them will be darker, and you'll end up with noise there, right? So what the temporal noise attempts to do is smooth that noise out by giving everyone a little bit of flicker so that over time they still look like they're all roughly the same amount of lighting, right? So by locking it in, what you're effectively saying is, well, now I'm going to have stark lighting changes, especially if we said we're going to use the same hemisphere for every point. Then you would see, like, you know, dark, 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 bright, 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 dark, dark, dark as you moved across. It would be like these little bands, right? It'd be really bad. Okay, but so maybe you don't care about that because that's not what we're doing, right? So that's fine. So now let's talk about releasing this constant, right? Instead of holding t constant, let's talk about what happens when a light moves through the scene. Well, now what happens is you get really bad behavior, because as this light moves through the scene, that noise that was previously distributed amongst pixels in the offline case is now distributed over frames in our case. Instead of having a little bit of flicker, but generally the right lighting amount, what we have is a stable lighting that appears to be dark. As the light moves across this ray, it becomes bright all of a sudden, and then as it moves away, it becomes dark again, right? So what you've done is you've pushed a flicker that was happening across frames that was just gentle and consistent, but reflective of the actual lighting, into a perfectly solid, very dark color that then gets very bright all of a sudden and then very dark again, right? And so what I'm trying to impress upon you is that when you are undersampled, if you do not want to have randomness in your initial sample, you're still going to get the noise coming out somewhere else. The question is, where is it going to come out? And at least for my taste, actually, if I have to pick between those two in the end, I'd rather have the flicker, especially because this is a nighttime game. Most of our light sources are going to be kind of flickery anyway. I would almost say the flicker that's more accurate on average is actually better than a perfectly stable but highly erroneous result all the time. And so that's really how to think about Monte Carlo. If you take randomness out of a sampling problem that really does have a very complex domain, you're going to push the noise somewhere. The question is, where do you push it? And almost the way you could literally summarize all of the techniques involved in Monte Carlo sampling, they are all about only one thing, and that is pushing the noise to the least objectionable place. That is all that all of them are about. Because there is no way to get rid of noise in a Monte Carlo problem that you're undersampling. Period. The noise is there. The question is, how do you push the noise to the place that causes the least objectionable visual artifacts? All right. Hopefully that clarifies things a little bit. Yeah. And that explains a little bit more about why it's not as simple as just saying, well, you know, we know that it's stable if we don't introduce any noise, so how about we just don't introduce any noise? It's like, well, that noise we're introducing is actually pushing noise that we don't want out of a place that it previously was, and it is important to push it out of that place. So we're moving the noise from one place to another, I think, to a place that we actually would prefer it to be in this case. But again, those are decisions you're free to make. Like I said, the important thing to understand is you're not getting rid of the noise, you're moving the noise always. So you have to just think about, are you moving it to the best place that it could go, right? So anyway, and like I said, you know, just looking at the way the lighting is working at the moment, I also do think like that flicker is not really objectionable to me if you imagine this light source is supposed to be a candle or a fire or a torch, right? It actually looks just fine. And so since this game does take place at nighttime, I would be inclined to leave that noise in so that we don't get some of the more objectionable artifacts in other cases as well, right? So that's probably the way I would summarize what's going on at the moment. Hopefully that makes some sense. If it doesn't, I apologize. But yeah, but there you go. So at the end of last stream time, I was talking about how to introduce blue noise onto the sphere, and you can see we made a sphere here that's a blue noise based sphere. And the questions that sort of we were working on was just how exactly we would allow this sphere to have its points vary so that we could sample neighborhoods around these points more efficiently, right? And the other thing that we needed to figure out is how we were going to cast coherent ray bundles. This, coincidentally, is also a problem that we would have if we went with a spiral-based sampling scheme. Same problem. We just need some algorithm on the back end to figure out how we cluster these into bundles that will probably hit similar geometry. Because the more disparate the bumble, that's good. I like that, a ray bumble. I guess, so if you put rays together that are coherent, maybe that's a ray bundle. But if you put rays together that are incoherent, maybe that's a ray bumble. Anyone? Any takers? Whatever. Anyway, so putting those together into a coherent ray bundle, so that, for example, these four are picked to send together because they go out in similar directions, as opposed to, say, picking this one, that one, that one, and that one, which would all go in completely different directions and never need to do any of the same geometry tests. Those will have significant effects on our performance because we're not doing any kind of ray re-up. We don't, once a ray has terminated, we don't really have a good way to re-stream it in. So all of our rays go through all of the checks that all of the rays need to do in the bundle. And that means that the closer they are to hitting the same stuff, the better, right? So that's, you know, that's where we're at. So, given that, yeah. I don't know if I just want to cluster things on this or what. We could do some kind of K clusters on this to produce some clusters of 4. I'm not sure what else we might want to do there. The other interesting thing about this is, you know, if you imagined tessellating this sphere and producing randomness inside it, that's another way to go. Anyway, I don't remember. I'm going to take a look here. I don't remember if we saved our, we did. So we've got, you know, a couple of different things here in terms of sphere creation, right? We have a couple of different ways in which the sphere is getting created. So one thing we might want to do here too is pull those out into, you know, routine for generating this for just for our own testing purposes, really. where we can kind of say like, okay, let's, have some different routines we can switch between while we're testing. And then obviously we'll only weld one in when we find the one that we definitely want to use. But, for testing, we may want to be able to be a little more flexible and switch between different tessellations of the sphere that we can actually use here, right? So I think the first thing I'm going to do is just get that into place so that we can do some testing with them. And that'll basically be something, in here that we can use to generate our sphere and play around with it from there. So if you take a look at the way this was working, we've got this like points buffer here. And what I'd like to do is just go ahead and make that, sort of an array out here we can play with separately. And I'll put a little sample point count out here as well. Although actually, I guess we always need to produce 64 of them, so maybe, that can just be something that happens only inside the routine, I suppose. That should be fine. And so then what I can do is I can kind of make ways of creating these ways of switching between which routine we want to produce the sample points. So for example, here where I've got all this stuff, I can grab this out like so, and then make one routine for the spiral and one routine for the blue noise. So here we go on, generate spiral samples or something like this, and generate Poisson samples. Poisson obviously being another way of referring to blue noise. Or Poisson, rather, is a pattern that happens to exhibit blue noise, might be a better way to say that. So here is our spiral sample. This is the spiral sample version we had here. Oops, put that in the wrong place. There we go. So if I take a look at what happens here, what I can do is make it so that we pass in the random series here. And that way, as it goes, we should be able to, well, maybe I'll do it this way. So as we do the sampling from the series, this will make it so it doesn't affect anything else, just uses that as the starting point. That should do everything else correctly, except when we go to do the push cube here, what I'm going to do instead is just retire the point. So in the destination, and what I want to do here is go ahead and hard code this. So what I want to do here is I just want to say, okay, as this goes through, we're going to take 64 samples. We're going to write them into dest. So the index is just going to tell us where to put this thing. We're not going to do that. And so the rest of this routine is fine as it is. It just goes ahead and writes us in there. We don't need the subindexing at the moment. Let's go ahead and get rid of that. And this. So there is our spiral without any noise, just the basic spiral that gets put in there. And then here is our Poisson version, which of course means fish in French. Just kidding. It's a person's name. Although Poisson is also fish in French. Doesn't matter. Point being, as we go through here, we will just replace it and write to the destination array exactly as we were writing to the one outside, but this time, we let it pass it in there. And yeah, I think that's really all we need to do. So those are our two ways of generating samples. And then when we generate those samples now, down here where we're going to draw them, what I can do is when we take the normal here, instead of doing any of this stuff to it, what I'm going to do instead is just say, all right, let's take the sample points that we recorded, or are saying we will record in our solution, and just draw whatever those were. Then what we can do is when you actually initialize the lighting, we can, not that I know where we do that anymore, but there it is. So when we initialize the lighting, we can initialize the lighting with one of these two, doesn't matter which one. But for example, if I want the spiral samples now, I just say, okay, why don't you do the spiral samples into my sample points buffer, and that'll be that. Let's see here. Just got to replace the point count with the fixed point count. And we should be good to go now. There we go. And let's take a look. So we should hopefully, if that was correct, we should now have the spiral sample in there, right? There's our spiral sample, which again is quite nice. And if we want to, we can switch that to our blue noise sample. And I could make a key that would switch between these as well. So, you know, if I go into world mode here, you know, we could bind the F9 keys to generate these. So this way, if we wanted to test, like, say, the difference between these two or something like that at runtime, you know, I can, or should, in theory, be able to. That did not work very well, did it? I should be able to do that fairly trivially. Where is my lighting? There it is. Seems like this is having some trouble inserting due to the cosine measurement. The other thing too I wonder here is if we should try to make this a more efficient generator, but that's kind of a separate issue, I suppose. So if we take a look at this here, the maximum cosine, it has to be higher than that. So we would like this value to be larger, yes, because the higher, I'm sorry, to be smaller, right? Because the smaller this value is, the better for us, I think. Because the closer it would be to 1. So I think if we make this value lower, we're in better shape, right? Yeah. So there we go. So the other nice thing about this is since it uses a random series that is updating over time, it also means we can generate as many of these as we want, right? Now, our spiral sample at the moment is not randomized, so it's pretty hard for us to tell about that distribution because we don't really have any randomness in there. Whereas the blue noise one, you can see we have a lot of random sampling options there, right? Because it'll always produce a random sampling there. I'm not sure exactly what we want to do with the spiral per se in terms of generating random samples from it. We haven't looked too hard at how that function works, so it's kind of hard to say. Anyway, regardless of any of that, once these things are generated, we could now actually try using them for our sampling just by feeding them directly in. Now, unfortunately, we don't have any, like I said, clustering of these. That's kind of the hard part now, is to figure out how we want to cluster 4 arrays together on any given one of them, right? Because neither of these two emits a straightforward way of figuring out which ones should be attached, right? Which ones we should be looking at. So for example, let's just go ahead and I'll show you kind of what this implies. If we take a look at how we're drawing these here, where we do the push cube, right? If we were to do that again here, where instead of drawing cubes, we actually just drew a line between the 2 points that's there. I'll show you what I mean. So let's suppose we take the previous point and this point and we connect the 2 of them with a line. So I do push line segment and I say, you know, I'm going to go from P plus normal A to P plus normal B. And then, you know, we just have some color for the line. Like so. Then what we could do is we can see, if we were to just group them in groups of 4, you can sort of see what would happen with our pairing, right? So looks like I've got something slightly wrong there. What did I do wrong there? Oh, I don't need to offset these. Sorry about that. They're offset from just that constant. They were being offset from each other. So if we take a look at the series, right, of points, you can kind of see that, you know, the way the spiral algorithm puts them in place is kind of nuts, right? It just goes like in this really unfortunate kind of bounce pattern. That makes it so that we really just don't know from one to the next. Well, what we do know is they won't be coherent, right? So it's kind of hard for us to make a lot of assumptions about that. Now, maybe we could do something where we just reverse engineer this pattern enough so that we can sort of say, well, we know that the first 4 points will all be kind of pointing upward, so that's fine. And then after that, you know, we know it's like, okay, well, take every nth point, maybe, you know, it's a little hard to say. So I'm not really sure about that one. The blue noise one is no better because it's going to be completely random, or should be, based on the way we generated it. Like you can see here, right, it's just kind of connected all over the place. So again, no real rhyme or reason to it. Now we could have generated this in a more coherent pattern. What we would have done is started with a point and branched out from that point. But even so, again, it could still form kind of relatively long chains that wouldn't be the closest clusters together. So, you know, again, I'm not really sure there's a lot to do here. The spiral pattern definitely gives us the most plausible way we could... it's the one we'd be most likely to figure out a rote algorithm for. Certainly more so than the blue noise. The blue noise definitely, you know... The blue noise would definitely be harder because there is no sort of obvious correlation there. So I'm not sure exactly what we want to do. We could take a look at the other one there. Whether we want to use some like, other kind of sampling patterns. There are like, let's see. I don't know if there's any other interesting points for Hemisphere saying, but like something that has a specific, let me see if this has some diagrams in it. Here's like a Halton sequence was the one that I was thinking of. Unfortunately, it doesn't seem like they don't have a diagram of it here. Yeah. Come on, people. Here we go. These are Hammersley, not Halton points. Those are related though. I don't remember. They're mostly the same, right? Let me see here. Again, mostly results, but not... Oh, there we go. So here's Halton points, and here's Hammersley points. These are the diagrams I think that we want here, right? So here we go. This is, I guess, random for comparison. And here are various p-values for the sequence. Which, I mean, that looks really nice, right? Here are Halton points with different bases on this, right? So I'm not sure what they were using for bases, right? Because these are 2D planes, so it's kind of hard to say how they were mapping them on exactly, right? That's the thing, is because Halton and Hammersley points are 2D tilings of points, and I'm not sure. See here, they're talking about basically how they're going to put them onto a hemisphere, right? So my question is not directly answered here, but I assume that the answer is yes. The reason that I mentioned these point sets more specifically is just because if you look at how these point sequences work, they're made to sort of progressively refine as you go further into them, which made me think that you would maybe be able to more easily figure out how to bundle rays together with them, right? Let me see. So for example, here you go. Red is 1 through 10, blue is 11 through 100, and green is 100 through 256. Now don't ask me why they're split in that way, I guess. But you can kind of see how they scatter fairly regularly, like amongst the sets. So you don't get, for example, a lot of red points next to each other, which is the important part here. So, you know, my thinking there was perhaps you could come up with something a little bit more regular for sampling the sphere and getting randomness around a particular point. So I don't know. So it may be that we want to investigate, you know, some other series as well that would be a little bit easier to make it go. You can see what the algorithm is here. It's not, you know, particularly complicated, right? And the other problem is it's kind of a recurrence relation here. So you kind of have to keep running state as you go, which I don't know how problematic that would be for us. Probably not really. Yeah, I don't necessarily know that we care too much about that anyway. But again, it's a little bit iffy. So I'm not sure if we want to go one of those routes. If we had infinite time, I think the best thing to do would be to implement lots of different series on the sphere and take a look at which ones were easiest to control. Given what we have at the moment, I guess what I would say, my first inclination is to take a brief look and see if the spiral version is possible to glean a little bit more structure from how it is being generated, such that we could more easily generate points next to each other, or know which of these points were next to each other, and then furthermore to jitter them to a certain degree, right? Or whether that is not going to be possible. And then furthermore to make sure that that can be done over time. So my first inclination is to take a look at that. I would like to maybe have some idea of the ordering of these points a little bit. So I think what I would like to do is introduce a color sequence that allows me to more clearly see visually what's going on with the points. I'm going to turn off the lines for now because I don't necessarily need that. What I would like to see instead is a sequence. So I'm going to introduce a structured sequence of colors here, so that I can see pretty clearly what's going on. So what I'm going to say is I'm going to start with red, go to green, go to blue, then I'm going to go to yellow, cyan, and white, black, 1, 2, 3, 4, 5, 6, 7, and, oh, sorry, I forgot one, magenta, white, and black. Maybe we'll start with black and end with white. So we'll go black, red, green, blue, yellow, cyan, magenta, white, and that way I can sort of see the colors as they go. So here where I would be drawing the cube, this is this whole thing. There we go. Here where I would be drawing the cube, instead of always using white, I'm going to use a color from the table. So what I'm going to do is I'm going to say, give me the color from the color table. That's whatever is indicated by the point index. And just wrap, you know. So this will, because we have 8, this will give us 8 sets of 8 permutations of this color table, basically. So now we can at least see a little bit about, how these colors go. I realized I forgot the trailing one there. And hopefully this will just let me see a little bit more about what the pattern looks like, because at the moment, right, obviously I don't really know. And so here's the spiral. And so if we take a look at this, pattern here, you can see that we start with black on the top, right? So, and we can almost see, you can really actually see the way these things curve down now that I look at it, right? So every 8 points kind of produces almost like a tri-strip pattern, right? Coming down here, which to me is actually very interesting. I could probably make interesting use of this to a certain extent. So let's take a look at the black spiral, for example. So the black spiral starts up at the top here. I'm going to move this down a little bit lower. So this black spiral starts here, and as it comes down, the initial point is probably going to be a special point. So, point 0 is a little degenerate, and I'm not sure exactly how we would process it. But one thing, let's ignore that one for a moment. If we ignore that top one, then what you can see here is that the black and blue, so that's here and here. So the 0 and 3 entries form a nice sort of tessellation there that you could do. You can make quads essentially between those if you had wanted to, right? So I guess, the one way to look at this would be, let's do it this way. So if we wanted to, we could even sort of draw that out, right? We could draw that pattern pretty directly. So let me actually do that just so you can see what I mean. So how many of these are there? 1, 1, 2. Well, 1, 2, 3. So one problem that you do get, though, if I look at this, right, is it kind of becomes too eccentric as it goes. So there's really no fill down here. 1, 2, 3, 4, 5, and then you got these two here. So it does seem like maybe, okay, so maybe that's barking up slightly the wrong tree there, right? So I may not be able, I was going to say that maybe that would be a pretty easy way to create regions that could be sampled in regularly, but not so much, as it turns out, because of the way those are not going to quite line up as they strip down the sphere. There's a little bit too much triangularity to it. Not that there's anything wrong with that, but it just makes it not as attractive as what I thought it might be. So I want to take a look too. Let's look at a couple other things now that I've got that, so it's pretty easy to see. When we generate our spiral samples here, if I twiddle this value here, so the 3.0, that's the value. We know that we want to at least be something above 2, right? Because we don't want the full sphere. If it was just 0, then, if it was just 1, we would get the whole sphere. 2 gives us a hemisphere because we're only going to go halfway down. So then the question is, well, what happens if we do less than that? It kind of scrunches up, right? Which is sort of one way of keeping us from sampling directions that are way non-contributory. That said, however, we're free to kind of pick anything in there, so I'm wondering what happens as we vary that value a little bit. So what I'm going to do here is I'm just going to say, let's have a sphere amount here. It's going to be 2.0 plus random unilateral, let's say 2.0. So now every time I generate, I'll get some coverage of the sphere that's a little bit different, right? So you can kind of see that, you know, I basically get the exact same points. They just jitter vertically, you know, pretty well, right? I would say. It's not awful. It does produce different amounts of clumping towards the top, of course, which is not really what I want to have happen, but it does at least jitter that direction okay. And then similarly, if I wanted to, I believe that just offsetting the theta would probably spin it as well, right? So if I said that I locked my sphere amount in as 3.0. If I take my theta offset and I do a random unilateral up to, say, 2 pi, well, I don't remember how this affects the series either, but I'm interested to see. Keep wanting to do that. There we go. And so, if we take a look at that, so that's not what I wanted, and you know what? That's because I did this originally, I think, as well. Theta is the wrong place to do that. So really what we want, it's a row offset here. So let's fix that. So that should spin us around. So that's better in terms of spinning, right? So now if I combine the two of these together, you know, in theory, this should give me something that generally covers the sphere okay. Hard to say, really, right? But it's at least not awful. Right? And if you take a look at, you know, one of the appealing things about this, obviously, is that it's pretty cheap to compute as well, right? There's not a lot of math in here. So we could actually compute this for every sample set, probably, and we'd probably be okay. However, obviously there's a little bit of an issue here, which is that we still have to do the one thing that I was talking about before, which is aside from the randomness, we actually need to figure out how to cast points together, right? So points that will end up being somewhat close to each other. So going back to the colors to see if I can do much with that, you know, if we were to cast, say, you know, points 0, 1, 2, and 3 together, those would certainly be reasonable. Then the next one here is this next point here. We would want to cast that effectively with probably with the red. We probably want to cast those 4 together, right? So we probably then want to do a fairly weird, like, striated pattern in terms of what gets cast together. It'd be like, what is that, point number 4? So it'd be like point number 4, then point number 9, 4, and then 9. And then the next two would be like the 8 offset from that. So I'm going to try something here, which is, again, kind of dumb. That's fine. I'm literally going to manually make the sequence as my first thing. Why am I going to manually make the sequence? Well, because it's easy for us to go read the sequence off now that we can see it. And so what I'm hoping is that if I manually construct the sequence, the series of numbers that emerges will be something that doesn't have to be manually constructed, right? That will be clearer. And then we can see whether it actually holds true across multiple jitterings as well, which we don't know if it will, but we hope that it will, based on how we did that, right? Okay, so let's take a look here. If we use our get current quads loop, if we use this this loop here, what I'm going to do, I don't know why we're still doing displacement because we don't actually use it. There we go. So what I want to do here is just have a point sequence that we're going to use instead. So here, what I'll do is say, you know, before, oops, we were doing it like this. Right? Where we just pick out the color and the normal, like so. Now we're going to do it slightly differently when we push the cube on here. What we're going to do is we're going to use the color as the color table, point index mod array count color table as before. This time it's going to be point index divided by 4, because we're going to take 4 points at a time to put them into clusters, because that's what we have to raycast, right? And then what we're going to do is we're going to take the normal out of our cluster table. And so here we go with cluster table. And inside the cluster table, we will just put the points that we want in there. So, you know, if we did nothing, probably do this a little bit more efficiently this way. And compile. So in this case, we should get exactly the same thing we were getting before, only now when we actually draw them, we should get, well, you know, we could get exactly the same thing if we just do this. Right? And so now what we're going to do is we're going to actually try to get those clusters to come out so that we get things next to each other by manually inserting these samples. So now I'm going to delete all this. So everything is just going to be 0.0. So we're just going to see, well, effectively nothing. We're just going to see the top point. So now let's try and work out what the cluster should be based on what we said we saw there. So here's like all the points. with their sequences intact. So what we were sort of saying is like, well, the first cluster, you know, if we wanted to sort of send a series of rays out the top that was good, I guess I would say maybe this set together makes some sense. I don't know how you guys feel about that, but that'd be 0, 1, 3, 5. 1, 3, 6. So if I switch back now and look at that, there's my cluster, my first cluster. Why is that black though? Shouldn't be. Oh yes, black is correct. Never mind. So let's take a look at cluster number 2. So if I wanted to send another cluster down now, going down the spiral, it's just pinks and reds from here on out, right? Well, I don't know. Those actually look a little more coherent, so maybe not. You know, maybe not. If we're sending those down together as the first tranche, you know, maybe the next tranche should be these guys right here. So the first 2 yellows, the first green, and the first white. You know? So yellow is 4. So the first 2 yellows would be 4 and then 4 plus 8, right? So 12. The first green and the first white. First white is 7. And the first green is 2. So putting these in order, not that we really necessarily want them to be, but just because that may make them slightly easier to see at first. So there's another one, another set. And again, those look pretty coherent. And you know, the other good thing about them is they look coherent no matter which randomization of the spiral I'm using. So that's also sort of encouraging to a certain extent. So that's good as well. All right, let's take a look at another one. And again, I'm just going to do several of these and see if I can see any pattern emerging, or some way that I could force a pattern to emerge, maybe by changing a little bit of how I assign it, or who knows what, right? Okay. So you know what I think might also be good, because as we get higher, it's going to be a little harder to see. I might do this. So this way I can see both at the same time. And what I'll do here is I'll just say, I'll push the cluster table version out slightly further, right? So now you can kind of see which ones of these are already taken. And furthermore, I could make that easier to see by maybe pushing the line segment instead. So what I could do here is say, like, okay, so now you can see the raycast clusters coming out as little lines, but you can still see the points that are involved, so that way we don't have to guess about which points go with what, right? So yeah, so looking at that, it's like, all right, can we make another bundle that would make sense here? And you can see the problem with the triangularity is still there. It's just, hey, oh well. Because as you pick ones, you're always going to be in situations where you get some that aren't really great. But here we go. Let's do some more. So the next two reds and the next two pinks would be fine as a cluster, right? So the next two reds, we've already used 1. So the next two reds would be 1 plus 8 and 1 plus 16, right? And the pinks, we've already used 1 pink. We've already used 6. So the next two pinks would be, again, 6 plus 8. And 6 plus 16. Right? Oh. 6 plus 16. So yeah, so something like that, right? And there they are. And so at that point, it seems like you then want to kind of switch a little bit. It looks like, then the next set of points probably wants to be blues. Maybe. It's really hard to say. Because if you cast, again, you get really eccentric there. I don't know if there's a way around it, right? But you could sort of do something janky there. And so, like, if I took these guys together, for example, that would be the next two purples and these two blues here. The problem is then what do you do down here, right? Because you're starting to get down to it. And you're going to paint yourself into a corner. So again, it's really hard to know how you would really get these guys together. I guess I wonder if there's some virtue to skipping point 0. You know what I'm saying? To skipping the top point. Because if you skip the top point, maybe that gives you a better alignment going forward. I'm not sure. But it could be that you could get a little bit closer that way. I'm not sure. That's a good question. Or if you did it like slightly offset, like offset by 0.5 or something like that as you go down, do you get something a little bit easier to tessellate? Because that's what we're effectively trying to do, right? So I guess I really just don't have an opinion about that. So I'm a little bit tempted at this point just because I'm seeing how hard this is going to be to keep these coherent. I'm also a little bit tempted to ask what would happen if we just were doing a straightforward polar sphere. So, because the spiral version requires us to use sines and cosines anyway. So we've already, if we were going to go that route, it's not like sines and cosines are a big deal because we're already doing them. So the question would be like, okay, if we were going to do a straight up one that was just lat long, right? what would that look like? So if we take a look at what that would look like, I would want to divide into rings the sphere, and I'd want to take certain samples around the rings, right? So in order to take certain samples around the rings, what we're going to basically say is like, okay, and I guess technically these might be considered more like cylindrical samples. I don't know how you want to say that. But if you imagine taking the height, so how many, if we said how many slices around the ring do we want? I don't know, maybe we want 16. Something like that. Then, you know, my height in this case is going to be something proportional to the slice amount. So maybe 1.0 minus the slice over the slice count, right? Something like this. And then, of course, I just want to take wherever I am on the disk, and I probably want, you know, this to actually be slice plus 1 in this case. But I want to take wherever I am on the disk, and I want to go out in my sine cosine fashion, right? So I've got my sine, and I've got my cosine. So now I want to place things around my slice. And again, I'm just going to do this rote at first, and then we're going to tune it. So we know we want 4 spokes around each slice. We don't actually want to do that eventually. We're going to want to do something a little bit more sophisticated, but for now, we'll just do it this way. And then I'll say, okay, for each of the spokes, you know, whatever my theta is for the spoke is just going to be whatever the spoke is divided by the spoke count. And so then in here, I can figure out what my x and y are. Don't ask me why this is still here. And so what I can do here is just say, all right, I've got my theta, like so. And I know that I'm just going to be assigning, as I go up, my height, right, of the slice is effectively telling me what my, well, let me just draw it for you, because I can't really explain this in a good way without pointing to a diagram. So if I look at a hemisphere, right, as I go up, effectively, if I assume that I'm going to be on like a particular height, then what that height effectively tells me is it tells me, you know, looking at my right triangle that I would construct here, it tells me what like sine theta is for this angle, right? And so if I wanted to know what this had to be, it would just be the cosine theta of that, right? Or put another way, Pythagorean theorem-wise, I know this is 1, and I know this is the value that I'm giving you as h. So I know that h squared plus whatever the thing is that I'm looking for, right? I know that h squared plus r squared has to equal 1. Well, 1 squared, which is still 1, right? So I know that if I just solve for how far that had to go out, I would know that it's going to be the square root of 1 minus the h squared, right? And I know I don't want it to be negative, so I know it's always positive here, right? So I know I could always figure out what that value should be, which means I don't really need a sine or cosine for that. So I know my radius in this case is always going to be equal to like the square root of 1 minus the square of the height. And furthermore, that's just, you know, that's only per slice. That's not going to change, right? So I know, in this case, I know what my z is. And in fact, I could just call it my z instead of my height, right? So I know what my z is. And then I know what my x and my y are because my x and my y in this case are just going to be equal to the circle, right? The radius that I want to go out times the sine and cosine for the sweep around. So at that point, I pretty much just have my normal. And I can just say, like, okay, whatever the point I'm recording is just going to be that x, y, and z, and then I'm done, right? I suppose this could just be called point count. Well, I guess I don't know what that is because we don't have that structure here. So generate polar samples is just another thing we could do here. And I can make it in world mode. I can make that be something that we look at. So now, in addition to spiral sample, blue noise sample, we also have whatever this sample is, right? Okay. So actually, and I think we did that pretty much correctly the first time, except for we forgot our tau term, so we're not doing the whole circle. But other than that, right, because this is just going to range from 0 to 1, and we need it to range from 0 to 2 pi. So there we go. So here you can see us sort of covering the hemisphere a little bit, right? But not a lot because we've got way too many slices versus spokes in this case. So what I want to do here, and I guess, you know, we could just reverse the numbering here or something, or do 8 and 8 or something like this. But what we want to do, hopefully you can see, is we need to change the slice count sort of proportional to where we are in the sphere, right? Because as we get closer to the top, we don't need nearly as many as when we're down at the bottom, when maybe we might want more, right? It's hard to say. So, you know, if we put this out the other way, then you can see we've got good sampling kind of around the base. But as we get up towards the top, we would like more here, but we don't have enough slices for it. And if we kept the slices going, they would get way too dense. So what we can do instead is say something like, oh, okay, maybe the spoke count is proportional to the slice count. So, you know, maybe the slice count can be something higher. But the spoke count adjusts as it goes up. So we've got, you know, some number of slices that go in here, and then as we adjust the spoke count, what we'll say is like, okay, you know, maybe the spoke count starts out at 4 and goes up to 16 as we go, right? So let's just take a look so we can tune this ourselves, and then we can make an expression for it once we have something that we've hand tuned to what we want, right? So in here with spoke count, we're just going to say it's the spoke table indexed by the slice amount. And so let's say we did something that was like, we know we've got 8 of these. So, you know, if we did something like this. All right. So let's say we did something like, I don't know. How are we doing here? That's 16 plus 16 plus 24, right? Oops, I've been admonished to never use calculator on the stream. There we go. So 16 plus 16 plus 24, right? So we have a little bit more to distribute there. So, you know, maybe we do something like that. So now we have 4 plus 4 plus 8. Well, 2 times 4 plus 4 times 8 plus, is that right? Plus 2 times 12, right? So, you know, I mean, I'm winging it, right? I don't have any particular opinion about why this would be good or not, but I'm just trying to come up with something that seems plausible, maybe, right? you know, maybe plausible. And that slice wants to be able to get a little higher. So I also think, you know, and since we're doing the spoke thing here, you know, also, so this 1.0 minus slice plus 1, I think maybe what we want to do is actually sort of put this inside here and say it's probably more like slice point, you know, 0.1 or something, right? So it's more like that. So we do get a couple up at the top, you know? And then furthermore, you can see how these are sort of distributed down as they go. You want to kind of be less at, you know, you want, I think this slice value also kind of wants to be more proportional, right? It wants to kind of go itself as a, you know, as a cosine or something. It wants to be counterbalanced. So it will sort of progress at a different rate than that. I don't know what the best weighting for that would be. I'll try like changing that to, you know, maybe a square root first, just to see if that helps. We'll try a square and a square root just to see what those look like. So that does shrink up towards the top, but not really the way that I wanted that to. Hold on a second. So if we do something like pi 32, that's going to be one hemisphere. We actually only want half of that. So if we were going to use like a sign to move it down, let's just take a look at what that looks like. Oh, that's... Did I do something stupid there? Let me... Oh, I did do something stupid. I put the slice on this. I'm just going to take this out. There we go. So I'm going to go ahead and take just this raw value. So slice over slice count. I'm going to take that ratio out just so I can get it in here more cleanly. There we go. And we're probably going to want to, like I said, offset this angle a little bit inside here because we're going to generate points right on top of each other there. So here's us, right, generating 4 points on top of each other there. I'm going to go ahead and so let's look at this first. That's still just, that weights the opposite way that I want it to. So it looks like what we really want here is a cosine weighting of these points, right? There we go. And that's much better. Again, so progressing a little bit further on this, so the interesting thing about the cosine too that's kind of nice there is that the ratio, when the ratio collapses, so if you look at where this is going to go, it's not going to go from 0 to 1, it's going to go to 0 to not quite 1. So z will not quite go to 0, but it will, the cosine term will hit 1 exactly, right? So what I can do here again is I think I do want to bias this slightly just to get it out of, to get that angle out slightly. I'm not sure how much we want it to be biased there, but we do want it a little bit, right? So you can see our first set being right there, yeah. And I don't really know, again, how far out we want that to be biased. There you go. Probably not quite that much. So now just looking at it, it looks to me like maybe we still have like too dense of a sampling in terms of our, and not enough here, like we got much bigger holes there. So I think what that tells me is the slice count probably wants to be reduced. So I'm going to reduce the slice count to 6. which means that we're going to remove like some of these here, right? So we're going to remove 2 of these, which means we could afford to distribute these points a little bit more, right? Hard to say exactly how we should distribute them, obviously. And that first one probably only does want to be 4, to be fair. This to be a little bit easier for me to work with. There we go. So if we've only got 6, we can maybe start to make these ones a little higher. There's something I might want to do there again with the sampling. Hard to say. We've got 4 more there, so I might say like that. And that's looking awesome, honestly. I feel like that's pretty good, right? And so, the interesting part about this then is just how do we line these up for casting purposes. And the reason that I kind of liked this tiling is because I feel like it's a little bit easier maybe to work with as far as alignment is concerned. Certainly the first 4 points just get cast together. That's not that tough. So the question more is like, the question is mostly just like, what do we want to do with rows where the row breaks happen? So from 8 to 12, from 12 to 16, and down here at the end, like I was saying, I don't know that, it would really help if we always had pairs. So, maybe one thing we could say is maybe you could do something like this. I'm trying to think of how to get rid of that there. So, that would be pretty easy to do. The problem with it, again, is you get some bigger holes in here. Now, one of the things that I probably should do, though, is we don't really want to be sampling that ring. That ring it's too much, right? And so we almost want to make sure we constrict our hemisphere to not really quite go that far, right? So we want to be sampling a little bit more like that. So let's keep it like that, because I think that informs our layout a little bit better as well. So, all right, let's keep pushing on that a little bit here. Let's try to get that top part cleaned out more. So let's suppose that we reduce the slice count further, because you can see we're still a little too tight here. So maybe we reduce the slice count to 5. So we have something more like this here. Right? And again, that emits a really simple covering almost everywhere except that last, that last pairing, which isn't quite great. And, I guess one thing we could do if we swapped those two, I don't know, it doesn't... I'm still not sure quite how I feel about that. because again, it's really tough to kind of decide how you group these points together. And there's some further complexities there. Like this is really very well structured, so we've got the best chance here of figuring out how to bundle them together, but it's still difficult, right? And part of the reason for that is when you think about how we're going to have to introduce jitter in here, well, we know that the jitter is proportional to this ratio, right? Because we know that this ratio is going in steps, and I mean here I'll just put it to this way. So if I introduce a random unilateral jitter here, it's pretty easy to see how we get the vertical jitter to cover, right? And we probably want to do that for every spoke as well. So this thing probably wants to live down here, which is a little more computation, but that's okay. Right? So you probably want something that goes like that. I mean, I don't know. Maybe you don't, because maybe you want to maintain more regularity. So maybe you want to make sure that the jitter can't actually produce points that close together, in which case you would sort of want to jitter them maybe more as a group. I don't know. That's a really hard call, and I'm not sure about it one way or the other. Because again, yeah, like the more that you do, that, the harder it is to know, right? Yeah, so again, just really difficult to say. And, that last point I just made is a really important one, too. The fact that it's like you want to jitter these points, but once you start jittering them, then you have to decide how are you going to maintain an even sampling despite the jitter. That as well kind of then, makes me think again, do we even want to do that, right? We've looked at several of these, and I'm not sure any of them really do necessarily exactly what we want. Like the spiral probably does. I mean, for the most part, the spiral always maintains the even sequencing, right? So the spiral is really the only one that I know of would do that. This one I don't know would really do that. Because again, it's going to want, if it's really going to be stochastic over the frame, it's going to want to jitter the points vertically this way. And there's going to, so the spiral is the only procedural one. The blue noise obviously will always do it, but the spiral is the only procedural one that would probably generate an even spacing every time, but that would still be coverage based. Now we'd have to test it to make sure it really does end up being coverage based. But there you go. So it seems like the only two options I can really think of at this point, based on this experimentation, that seem viable to me are either figure out some way to actually cluster the spiral procedurally, which I don't immediately see, but if we grind on it, we may find one. Or the other option is take just precompute a bunch of permutations of them, and use those permutations. And we could perhaps rotate the permutations as well for extra permutations, because we know that if we spin the sphere this way, we don't change its distribution at all. It's still the same distribution. So for example, blue noise or spiral, if we generated a bunch of different ones of those, clustered them actually using a routine that just looked for the clusters, so we don't have to have a procedural way to do it. If we did that and then just picked a random series out of our batch and randomly rotated it, maybe that's just better. And then we could literally use blue noise at that point. So we could actually have something that was a truly blue noise, not the spiral sample, which is not really blue noise, right? So I don't know. but I'm kind of leaning towards that. That to me seems like the sanest way to go. And I think the bonus of that method is also that it doesn't really matter how we come up with those distributions either. So it kind of has the nice point of like, all right, if you want a spiral or you want blue noise or you want something really difficult to compute, it doesn't really matter because we can just pre-compute a bunch of them and just pull one out. Because that gets us out of the business of caring how long it takes to produce the distribution, which some of them, like the spiral, don't take very long, but others like blue noise might take very long. Even if it's optimized, it may still be a little bit too expensive, right? So I think that's what I like best, honestly. I think that's what I like best. So I think that's what I'm going to try. It's not super hard. The only thing we have to write that we haven't written is the clustering algorithm. And the only thing the clustering algorithm really needs to do, although it is hard, but it doesn't need to be perfect, it just needs to make sure that every 4-point set tends to be fairly correlated. And maybe if one of them's wrong, it's all right, but in general, we don't want like lots of wrongness there, right? So yeah, I mean, that's just going to be, there's a sample point array and we've got, some number of them. I don't know how many of them we actually want to do, but, let's say we took 16 of them or something, and then you rotated them. That seems like a very large number of permutations, right? Furthermore, these sample points, if we get down to it, we don't really need to store three whole floating point values. We can just store 2 floating point values because the z value is always positive and it's always the square root of the 2 other values minus each other, right? Like we know that x squared plus y squared plus z squared always has to be equal to 1. So we don't really have to store that value. So again, in terms of like, if we just want to make sure we're always minimizing the amount of like bandwidth that's necessary to use pre-computed sample points here, not only is that true, but also we maybe don't even really need that much precision. So we could also decide to just store it as some more compact representation as well. So for example, we could store them as 16-bit values instead of 32-bit values. We know their range is always between 0 and 1, so it's not like we even need floating point. For that, we can just use literally 65,000 divisions of the 0 to 1 range and probably be fine with that as well. So I feel like we've got a lot of options here. So I'm fairly comfortable with this as an option. So I think that's okay. And furthermore, we can make sure that these sample points are lined up nicely for however we want to load them. So if we just go briefly back to where we're actually sampling these, and you can see here where we're picking our random bilaterals and so on, right? So the way that has to work at the moment is it's picking up the delta there. So it wants to load in it wants to load in forward time, right? So we can also, kind of make this a little bit sort of nicer on us by saying that, you know, we actually just want 16 of these and we want them to be pre-packed in the load format. So, you know, that is also another way that we can get a benefit here, right? So let's go ahead and try making our algorithm work this way just temporarily. And the way that I think we can do this is just by saying, look, if we know that this is a rollable value, then we can automatically make a mask for it. So in here where we go through casting our rays out of the sample points here, what we can do is sort of say, well, all right, don't do this anymore. Instead, just load these out of the sample point array. And the ray index mask in this case is just 15, right? But we'll play with that a little bit more. Let's get rid of that. So in here, then we just have to load out sample 40x from there, and I think we're pretty much done. And in fact, this garbage doesn't have to happen anymore either, I don't think. Right? Because these would already be ready to go. So I think that's pretty much it. And so if we just now initialize those with useful values, then I think we'd probably be good. Obviously, we need to know which one of these we're using here, and that one could be based on the sample point index, for example, as we step through. So maybe this is sample pattern mask as well. And so as we step through those, we would get different samples out. And so what we could try, first of all, is just now when we init our lighting in here, what we could do is just make our lighting code do this to start with, and this will replicate our existing lighting to a certain approximation using the tables instead. So we can just, double check that. Actually, I didn't really need to do that, did I? Because I'm going to put this inside another for loop in a second. So here we have our pattern index. And that's going to be proportional to however many there are in the pattern array. And then there's the bundle index, and the bundle index is going to be proportional to however many there are in, like, say, one of these. And then we're going to produce those random ones, and then in here, instead of just using it, we're just going to do a reassignment back to the sample points. And so then when these are stuffed here, after we're done with that, I think all we really need here is a way to get our series out. So what I'll do here is say that the random series equals solution series. And that should be the end of it. Okay. So I'm going to not do the drawing for a second here because that's sort of another part of the problem. What are we complaining about? Sample point n. Okay, so this one, sample point n, is just saying what direction the sample point had to go here. Oh, that's a good point. So we are going to have to rotate these to align with the sample point, though. This is a good point. So we do need a little bit more code there. It's not going to be quite as drop-in as I was about to say there, but that's okay. So the sample point n, in this case, though if we want to produce patterns that are just basic patterns, then what we're really looking to do here is that sample point n is just the normal we want these to all be pointing along. And of course, we know what that actually is in this case. We know because we want it to just always be pointing upward, right? So really, in this case, when we're looking at the less than or equal to mask, we only really need to look at the z, and that's, so we don't need this inner product anymore. All we really need to do is say, well, we want to basically pick between the positive and the negative versions of these based on whether or not the z was going the right way, and that's all we needed right there. So that's all that's doing, and that's fine, right? So let's go ahead and nerf this out temporarily, but I'm going to put it in. I'm going to put it back in. I just want to nerf it out for a quick moment there, because yeah, we're going to have to fuss with it a little bit more. All right, and so our lighting is going to be a little bit broken when I first run this. The reason for that, like I said, is because it's not aligning with the normals. So it will sort of do lighting, but it will be gathering like backwards and doing other kind of odd stuff, right? And so first we have to correct that part of it in here where I grab out those sample points. Here, so once we have that, we know that the sample point normal, which is this thing here, we know that we need these things to be aligned along that sample point normal. And so in order to why did I bother masking this? This is dumb. We know there's exactly that many. Yeah. Yeah, that was stupid. Anyway, so looking at this, we know that once we have one of these, we now need this to be oriented along the sample point normal, right? And if we look at the sample point, I believe we sort of have this nice factor here that the x-axis and the y-axis are known to us, which is pretty important actually, because that's the only way that we could trivially construct things that we know face out that hemisphere. So generally speaking, when we do this sample here and we have the sample for x, that's aligned in like the reference coordinate frame where z up is 0, 0, 1, and then our x and y axes are 1, 0, 0 and 0, 1, 0 respectively. And so if we want to transform this, what we need to do is effectively create an equation here that reinterprets it along those lines. So we kind of need something that's going to look like this, that reinterprets these as they should be along the various directions. So this is the sample point n here, and we need the sample point x and y here. Whoa. I don't know what that was. Like so. And so in here where we do x and y, that's just these axes. And I think that's really all we need to do to make sure that they point in the correct direction. So yeah, not necessarily a huge deal, but something we definitely need to do. We don't know if that's actually correct yet. So we would need more, we need to actually test and draw these things to make sure that we're doing this properly. But that's basically what we need to do, right? We need to basically take the samples that we've baked in there, and we need them to be reinterpreted along these axes. Let me, it's not sample point x and y, it's the x-axis and y-axis, which is different. So I just want to make that a little clearer there. So as we pull each one of these out, again, the sample point index, this is just giving us which sample point array we actually want to look into. And the array index is just 0 to 16, which are the 0 to 15, the values in there that we've actually stored. And that should be usable, right? That should be giving us something similar. It looks a little off to me. So again, I think we didn't quite, we don't quite have the transformation exact yet. That's my guess anyway. But it's pretty close. So tomorrow what we'll do is we'll draw it, and then we'll also actually generate ones that have good distributions. And we'll be able to then verify what we want. I'll take a quick look now just to make sure there's no obvious bugs, but then we'll tackle the rest of the debugging and the improvement itself tomorrow. So looking at this here, I mean, really, the other thing about this here is we'd rather just have this be completely randomized. It's all right, but it looks fairly reasonable to me, though. So I don't see anything obviously wrong with it. So I'm going to go ahead and go to Q&A today, and we will take care of the debugging of it tomorrow. While I'm waiting for questions, I noticed, as Sylvan said, by the way, I mentioned this on Twitter, but the easiest way to compute a cosine distribution is to start with a 2D disk distribution for xy, then compute z by projecting to a sphere. That seems pretty good. I guess what I would say is what we could do, let's assume that this idea of pre-computing the points is a good idea. One thing we could do is generate a bunch of blue noise disks and then project the z so that they end up being cosine weighted. That seems pretty compelling to me. I guess I think that's a good thing to try. Assuming that this pre-computed version is a good way to go, then we could pre-compute like 16 blue noise disks and project them up using the square root. Do you have some resources for researching different game system architectures in C? I'd like to focus on the data layout. I do not, really. I mean, obviously, there's the game architecture book by what's it called? Game programming, game engine architecture, I think, by Jason Gregory. And he's doing a 3rd edition, I think, of that now as well. Okay, maybe. Yeah, there it is. Yes, 3rd edition. So when is that coming out? I don't know when that's coming out, actually. Yeah, I don't know. I don't know what to say necessarily about that, but that's kind of I would say one of the basic reps for it. A lot of these things, unfortunately, most books that kind of talk about these sorts of architecture things, they post-date my having learned how to make engines. So I don't know what's in them because I don't read a lot of game architecture books now. for obvious reasons, I already kind of know most of the things I like to do. So when I want to look something up, it tends to be more pigeonhole. So if I was going to look up something in a game engine architecture book, I'd be looking at a specific section. I wouldn't really be reading the whole book typically anyways. So one of the problems is I don't have a lot of... I can't like go back to when I was learning and go, oh, here's the books I liked, because there really weren't any good ones at that time. There may be good ones now, and I just don't know what they are. But that one, Jason Gregory obviously has a lot of experience with these sorts of things, so I would be pretty surprised if the book didn't have good information in it, I guess one way to put it. Jeff Lander as well, obviously. I don't think I know the third author. I think I know there was a third author. I know two of them, and I don't know the third, I don't think. Yeah, so Matt Whitting, I don't know who that is. Although I guess it looks like Jeff Lander just wrote the foreword, so maybe it's all Jason. But Jeff Lander is also a very good programmer. Most people don't know who he is. I think probably, but he's very good, and he's been around a long time and done a lot of really good work. So, apparently he didn't write the book, so it doesn't matter, but the foreword is probably also good. Let's see. Blackburn 1911. What should I do every day to become a good programmer? Well, I guess I would say that programming a lot and exploring new ideas is really the most important stuff, right? Like, I feel like the two main ingredients to being a good programmer are programming a lot. So, at least 6 hours a day, every day, your whole life, right? You can take weekends off if you want, is step number one. And number two is always be looking for new things. Like, don't assume that the way you did something last time or the way someone told you to do it is a good way. Explore new options and think critically about how you can improve things. And that process takes a long time, but that's the only really way to get good, right? It's the same as getting good at anything else. How do you become a concert pianist? It's like, well, you play piano every day and you constantly try to think of new ways to interpret a piece of music that sound better or more interesting, right? I mean, it's just a lot of hard work. And most people who are bad programmers, unless somehow they were born with brains that literally just can't be good at programming, one of those two things isn't true. Either they don't program enough or they don't try hard enough when they're programming to do new things or look at things differently. Because it really is an active process. Like, you don't just sit down and do it. It's an active process of going, I want to make an improvement here. I want to get better at doing this thing. So I'm going to try something new and see how it works. Because that's the only way you get better, is by trying something new and seeing which ones work. And sometimes they don't work. You see that on Handmade here all the time. We try something new, it doesn't work, right? That's the cost of finding a good way, is having to have gone down bad ways and recognize that they didn't work and then start over. That's just how new things happen. Otherwise, you're just kind of a monkey, right? Typing in stuff the same as everyone else. And that doesn't really... isn't really worth a whole lot, unless if you just want a job, then it's fine. But if you're trying to really be good, that's not good enough. Elfec, do you use templates in the code? No, we don't use templates. I'm programming my first game in 2D as an intake assignment for my next education. The game uses an entity component system, but now I'm stuck because I want different entities to have different animations for different situations, but I don't know how to implement that. My question is, how do I go about that without writing different sprite components for every different entity type? All sorts of information is welcome. So I guess what what I would try to encourage you to do here, because if this is for educational purposes, is I would encourage you to take a step back and think about whether the structure that you've imposed, or that your assignment more perhaps, has imposed on the question you're asking, right? And this again is one of the really big problems I have with object-oriented programming as well, But it's not really a problem with object-oriented programming per se, it's just that it's particularly pernicious in that type of programming. But it extends to all types of programming if you let it, and it's always bad. And that is thinking about the answer to a question in terms of artificial constraints you have put on the solution, because either someone told you they were good ideas, or because you thought they were good ideas. And it's always important to re-examine those. So let's take your question apart more specifically and look at what you asked. You said, I'm stuck because I want different entities to have different animations for different situations, but I don't know how to implement that. Okay, but you absolutely do know how to implement that because it's trivial, right? So more specifically, what you don't know, what you actually don't know, is how to implement different animations for different situations in terms of this structure you've imposed on your code somewhat artificially, right? Because if all you want to do is have different animations for different situations, we all know how to do that, right? Whatever you've got, you could just have a thing in here that's like, all right, enum, my different situations, situation 1, situation 2, situation 3, right? And then you've got something that's like play animation. Should put in here. Right? So we all know many ways in code to just sit down and type in something that has different responses based on some parameter that we just set on an entity. Like, hey, this entity, I'm just throwing a thing in here that says it plays this animation for this circumstance, right? You just literally put that in. And so the question that you are actually asking here is, in some weird construct that I've created where I've preset I'm not going to do that thing that is very straightforward and obvious, how do I do it? Well, the answer should be rethink how you're doing it. If it's not obvious how to make a special case in your system, there's something wrong with the system. And that system should be augmented to include an easy way to add a special case, or it should be thrown out because it's just bad. And again, that's the problem I have with a lot of object-oriented systems, is they make it so that the obvious way to type something in is like frowned upon or bad or just straight up impossible, because they've made this ridiculous collection of objects and concepts that are impenetrable to actually writing what's supposed to happen. Writing what's supposed to happen explicitly is not bad. It's in fact optimal. And the goal of any system should be to make it as easy as possible for the programmer to say explicitly what they wanted. And every additional step you add to a system that forces the programmer to do something other than the obvious, hard-coded correct answer is actually bad, not good. What a system is supposed to do is make it easy for the programmer to put in special cases and to apply cases to as many useful ways as possible. So if they have a thing that's like, hey, anything that sort of acts like a sheep should play the sheep animation when, chased by a wolf. The goal is to make it as easy as possible to write that down. It is not supposed to be to prevent the programmer from saying explicit things. And as soon as you get yourself into a system where you don't even know how to say explicit things anymore, that system is bad. Full stop. So it's important to understand these pieces. So I don't know exactly what your system looks like right now. There's two situations you may be encountering. One is that you've ended up with a system that is simply too unwieldy, and it should be torn apart a little bit and made simpler, right? And made more flexible. The other is that you just don't understand the system that you've built well enough, and this happens to everybody. It happens literally to everyone all the time, which is when you first start building a system, no matter how good you are, you have no experience with that system, so you don't really know how to use it yet. It may be that you're in a situation where your system actually could express this very easily, but you just don't understand how. And so you need to look at that a little bit too. And so you need to figure out which one of those cases you're in. If you're in the case where you just needed to like sit down and think about it a little bit more, and the system actually expresses this cleanly, great. If not, you need to back up and you need to say, how did I paint myself in this corner? Vicar said he played with the spiral and had problems with the angular fall off. I could see that. That's why I kind of like the idea of pre-computing the distributions more. But we'll see. 3D Gamer, first timer here. From what I saw, it looks like organizational wise, a lot of things are bundled together in your code. How do you handle organizing a lot of code in general? Is it a C++ thing to have so many things together? I'm just kind of used to having small pieces of code. No, that's not really a C++ thing. There's lots of C++ programmers who break things down into incredibly tiny parts. That's just how they like to do things. In my opinion, I think that's usually bad. The reason is because the more interrelated code is, the easier it is to play with it. You can just quickly like rewrite parts of it and do whatever. So I tend to postpone breaking things apart till much later in the process than most people. Now that doesn't mean that I actually leave them all bundled together forever, because I usually don't. So eventually when I get to the part where I'm totally sure I know exactly how something works and I want to kind of put my stamp of finishedness on it, I will then tend to break it apart a little bit more into pieces, possibly if I want to do some testing, possibly if I want to do some optimization, because sometimes you need to do that, and so on. But I think typically there's a lot of fetishism around breaking code into small pieces, and I don't really approve of that. If you don't have a reason to break code into a smaller piece, you typically shouldn't, because it just makes it harder for someone who's coming to the code to edit it and read it to know what's going on, because now they have to look across many, many small pieces of code to figure out what's happening, rather than just stepping through the code in series and seeing exactly what it does. And furthermore, it creates artificial divisions in the code that don't actually exist, that then can create problems when you're trying to modify it. So typically I think code should be broken into pieces that are as small as necessary, but no smaller. And I think it's important to remember that but no smaller part, because a lot of people just break things into small pieces of code for no reason. I don't think that's generally good. Case, I just want to say thank you for everything. I started to watch you in 2014 when I graduated university. You taught me more than all my teachers there. I love game development and love programming all because of you. Well, that is a very kind thing to say. I very much appreciate that. And I hope that you continue to love programming, and it continues to be something that you find interesting and enjoyable throughout your life. Did I find an answer to my questions in my blog post, the particular blog post in question? I'll bring it up here. Is our register name still useful? No, I haven't. This is a blog post that's just about hardware. It's not an educational blog post. It's just a question that I posed to hardware designers, and the question was simply, do you think that register names are still the best way to communicate a program from a compiler to a CPU, in light of the fact that nowadays hardware doesn't really use registers in the same way that it used to. It used to be that register names really were registers, so it was the CPU was literally getting exactly what it should do from the instruction stream, and registers names I think make a ton of sense there. Nowadays, what the instruction stream is telling the processor is actually not that, because the processor typically has lots of versions of any given register in flight at a given time. Either in a hyperthreading context, the registers are wide across threads. In an out-of-order processor, they're often referring to different things at different times. So the same register name is actually referring to different states throughout different parts of the micro retirement and all these sorts of things. So this was really just a question like, are register names still useful, or is there some other naming scheme we should be using I know like the mill CPU proposed one. I didn't think it was a particularly interesting proposal. I think there's other proposals that might be more useful. I gave an example of one, which was like a stack-based register naming scheme. I don't think just using memory directly makes sense, and the reason for that is because memory names are too long. They're up to 64 bits long, and that's simply not a concise way of producing an instruction stream, because instruction streams need to be compact in order to avoid too much cache decoding and so on. So I asked that question here in this post. I have not received any real answers from hardware designers yet, probably because they don't read my blog, because why would they? There's nothing in it about hardware, but I still wanted to post it anyway. If I ever do get any answers, I will be sure to let you know. Fort99, you mentioned not using templates. Do you use any code generation or metaprogramming at all? I do in our actual code base at Molly Rocket. I do not use any metaprogramming on stream on Handmade Hero, only because I wanted to restrict this to kind of C++ programming. For this particular stream, metaprogramming is a whole nother thing that you do. It's a completely different discipline, largely unrelated to anything we're doing on the stream, so I didn't really want to take on that topic here. Every time I am designing the data layout of a game system, I get very happy inside. Is this normal, or should I see a psychiatrist? Also, I absolutely love the sections about the entity system and game design decisions. I don't know if it's normal or not, but it's probably good. Anything that makes you happy on the inside while programming is good. Sneaky Bob, how much more optimized do you think you'll be able to get this lighting code once you've sorted out this bundling? I don't know. It depends whether we do a GPU version or not. And we got to look at it a little bit more. But right now, we just want to smooth out our sampling a little bit. And that's not really optimization. That's just getting a little bit higher quality from the same optimization. I'm a programmer with 3 years of experience. What would you recommend for someone with my experience level to do to improve as a developer? I've been trying to learn new things outside of work while avoiding breaking the non-compete part of my contract. Yeah, I would say that taking up side projects that you just use purely for your own educational purposes and experimentation are actually very good things to do. It depends on what you're interested in learning, but you know, if you want to learn graphics, write a ray tracer, for example, would be a good idea. Things like that. But it really depends on what you want to learn. Pick a side project which aligns well with your goals. Do you want to learn more math? Do you want to learn more programming structure, architecture? Do you want to learn more sound programming? Do you want to learn more rasterization? Do you want to learn more physics? You know, make the project fit the main thrust of what you want to get better at, just your own personal preference, what you want to get better at right now. That's what I would say. Do I still use my Amiga? Well, use my Amiga may be a strong term. I don't really use it for any real purpose. Do I still fire it up occasionally to marvel at how much better it is than this piece of garbage Windows 10 CPU sitting in system sitting in front of me? Absolutely. But really, I just get depressed because I realize that, you know, thanks to Microsoft, we've spent 30 years getting absolutely nowhere, even though the hardware we have is absolutely amazing. Any good resources about game development that is surely not language or platform specific? I don't know. Couldn't say for sure. Sorry. All right, and with that, we have come to the end of the questions, so I will go ahead and close things down. Probably should get rid of this here before I do, so we don't check in that code to the GitHub in a second here. Everyone would pull the changes from today and be like, what is this? Thank you, everyone, for joining me for this episode of Handmade Hero. It's been a pleasure coding with you, as always. I think we've pretty much settled into how we want to do our sampling, so tomorrow we will try to improve that by actually implementing some of those, like maybe putting our blue noise scheme in there or whatever, and then seeing how that does when we put it into actual practice in the game. So hopefully you'll join me for that tomorrow, same time, same place. Until then, if you do want to play around with the source code, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can play around with it yourself and do your own experimentation. Maybe you can find some good ways to do lighting sampling. In the meantime, that will be interesting. That's about it for today. I'll see you back here tomorrow. Till then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.